Battery swapping is a method of recharging electric vehicles by exchanging a depleted battery for a fully charged one. The idea is to deliver a convenient refueling experience for electric vehicle drivers, comparable to a quick stop at a gas station. Battery swapping only takes a few minutes, making it significantly faster than traditional EV charging methods, which can take anywhere from 30 minutes to several hours. Battery swapping definition. Battery swapping is a way of replenishing an electric vehicle by replacing a depleted battery with a fully charged one on demand, rather than plugging the vehicle into a charging station. Why is battery swapping important? With rising interest in all-electric and hybrid cars, new technologies like battery swapping are being developed to help ease drivers through this transition. In addition to reducing a vehicle's downtime, battery swapping promotes widespread EV adoption by addressing concerns related to slow charging speeds, range anxiety, and enhancing overall battery maintenance. Related reading. Will charging an electric car ever be quick and easy? How does battery swapping work? Automated battery swapping stations are made to service four-wheeled electric passenger cars. Manual stations are designated for two- and three-wheeled electric vehicles, like scooters, mopeds and rickshaws. Automated battery swapping. Drivers pulls their electric vehicle into a designated swapping bay, where an automated system checks the model for compatibility with its battery inventory. Once the vehicle is positioned in alignment, the underlying platform mechanically lifts a few feet. A robot arm then locates the depleted car battery in the vehicle's underbody, unlocks the battery compartment, removes the depleted battery and installs a fully charged one in just a few minutes. The vehicle is lowered, and the dead battery is put on charge at the station for future use. Manual battery swapping. Drivers park in a designated swapping bay and check in, either manually with a station attendant or via a digital app or kiosk. The station staff or system verifies the condition of the depleted battery, and checks the EV's compatibility with the available batteries. The depleted battery is removed from the vehicle and plugged into charge. A compatible, fully charged battery is pulled from a wall of battery slots, then manually installed. For both systems, drivers can choose to pay per swap or sign up for a battery as a service subscription membership on a recurring basis. Related reading. 7 new battery technologies to watch. Benefits of battery swapping. Battery swapping has sparked interest over the past couple decades for the following reasons. Fast charging speed. Battery swapping stations cut EV charging times from hours to a matter of 3 to 5 minutes and, with advanced infrastructure, that could be reduced even further. Take for example Beijing, where there are more than 250 active battery swapping stations, which completes a battery swap service in an average of 1.5 minutes. And in San Francisco, startup Ample has halved the time it takes to swap out a battery from 10 to 5 minutes with its next generation of battery swapping hubs. More convenience. Battery swapping stations eliminate the long wait times of traditional recharging, bringing drivers back to the familiar experience of making a quick pit stop to refuel. At automated stations, the entire process is so seamless that drivers remain in their cars from start to finish, similar to an oil change. China-based EV car manufacturer NIO claims that it delivers a fully charged battery pack almost every second, completing about 79,000 battery swaps per day, 50 million cumulative swap in total across its network of stations. Reduces range anxiety. Even though there are about 140,000 public charging stations nationwide, the fear of being stranded because of insufficient battery storage, known as range anxiety, is one of the foremost barriers to widespread adoption of electric vehicles. With more swapping stations, drivers would be able to confidently commute longer distances without having to track down charging points or add hour-long detours to their trips in order to recharge. Energy efficient. Centralizing EV charging at battery swapping stations allows batteries to be charged uniformly, at a slower pace, which extends their lifespan and reduces electronic waste. It also enables stations to limit charging to off-peak hours, or dynamically adjust energy consumption based on demand during peak periods to reduce strain on the local power grid, especially if locations are strategically selected. Related reading: 23 electric car companies shaping the future of travel. Challenges of battery swapping. As with every new technology, there comes a range of potential drawbacks. Lack of standardization. EV manufacturers do not standardize their car batteries, making universal compatibility difficult. With varying designs, sizes, and configurations, the scalability of swapping stations may be limited to a certain capacity, as each would need to stock their inventory with multiple battery types from different generations, increasing costs and complexity. Infrastructure setbacks. Today, battery swapping stations are sparse. Aside from some notable traction in China and India, the infrastructure for these networks remain underdeveloped in most parts of the world. EV charging stations are also becoming more efficient, casting doubt on the demand for battery swap stations at all. High cost. The average cost to build a passenger car battery swap station is around $500,000, according to CNBC. That's significantly higher than the cost of installing a two-port charging station, which typically range from $200,000 to $300,000. Battery ownership concerns. Battery swapping requires consumers to relinquish ownership of their car batteries, which may deter those who prefer full ownership of their vehicle from participating. Drivers may also worry about receiving older or degraded batteries from a swap, potentially affecting the performance of their car and overall resale value. Most battery-powered devices, from smartphones and tablets to electric vehicles and energy storage systems, rely on lithium-ion battery technology. Because lithium-ion batteries are able to store a significant amount of energy in such a small package, charge quickly and last long, they became the battery of choice for new devices. But new battery technologies are being researched and developed to rival lithium-ion batteries in terms of efficiency, cost, and sustainability. Many of these new battery technologies aren't necessarily reinventing the wheel when it comes to powering devices or storing energy. They work much like lithium-ion batteries do, just with different materials. How do lithium-ion batteries work? Lithium is stored in the battery's anode, the positively charged electrode, and the cathode, which is the negatively charged electrode. A liquid electrolyte, or separator, transports positively charged lithium ions between the anode and cathode, the movement of which helps create free electrons in the anode. As a result, a charge is built up at the battery's positive current collector, which flows through the device to the battery's negative current collector. When powering the device, the anode is transferring lithium ions to the cathode, and when charging, the cathode is returning them. While lithium-ion batteries have come a long way in the past few years, especially when it comes to extending the life of a smartphone on full charge or how far an electric car can travel on a single charge, they're not without their problems. The biggest concerns and major motivation for researchers and startups to focus on new battery technologies are related to safety, specifically fire risk, and the sustainability of the materials used in the production of lithium-ion batteries, namely cobalt, nickel and magnesium. New battery technologies. Here are a few new battery technologies that could one day replace lithium-ion batteries. New battery technologies. Solid-state batteries. Lithium-sulfur batteries. Cobalt-free lithium-ion batteries. Sodium-ion batteries. Iron-air batteries. Zinc-based batteries. Graphene batteries. An overview of solid-state batteries and their advantages. Video, Undecided with Matt Farrell. Solid-state batteries. How do they work? Instead of relying on a liquid or gel electrolyte, solid-state batteries use a solid electrolyte. These solid electrolytes are typically ceramic, glass, solid polymer or made with sulfites. How will they be used? Following its announcement that it would test solid-state batteries, BMW received its first batch in November of 2023 from Solid Power and has continued to work on prototypes. However, the company won't be able to produce solid-state battery-powered cars until after 2030. Meanwhile, Toyota could launch solid-state battery-powered cars as soon as 2026. Solid-state batteries are already being used in pacemakers and some smartwatches, and devices like smartphones and tablets could soon follow. Pros and cons of solid-state batteries. Compared to lithium-ion batteries, solid-state batteries are more efficient, packing more power with the same size battery. As a result, EV batteries could become more compact, charge faster and weigh less, which could increase range. Solid-state batteries are believed to last longer with up to 7 times more recharges during their lifetime, according to Car Magazine. They are also believed to be safer because the solid electrolyte material is fireproof, unlike lithium-ion batteries, which are known to pose a fire risk. Currently, the one drawback to solid-state batteries is how difficult it is to scale a technology in its early stage for widespread use, given testing and limited production capabilities. In addition, it takes time to engineer and verify the performance of solid-state batteries, contributing to delayed release dates for some companies. How sulfur can be used to create safer, longer-lasting batteries. Video, Undecided with Matt Farrell. Lithium-sulfur batteries. How do they work? This new battery technology uses sulfur for the battery's cathode, which is more sustainable than nickel and cobalt typically found in the anode with lithium metal. How will they be used? Companies like Conemux, an electric vehicle battery manufacturer, are working to make lithium-sulfur batteries a reality, aiming to have them commercially available by 2028, according to the clean energy news site, Clean Technica. There's even hope lithium-sulfur batteries could be used to power aircraft and trains, along with energy storage, according to Electrek. Pros and cons of lithium-sulfur batteries. Lithium-sulfur batteries are believed to be more efficient than lithium-ion batteries, which could increase the range and storage capacity of electric vehicles. Additionally, sulfur is affordable and abundant, which could mean lower costs. And since the manufacturing process for these batteries is like the one used for lithium-ion batteries, the same facilities could also be used for production. Advancements in lithium-sulfur batteries have also resulted in ultra-fast charging and made them useful for raising the storage capacity of renewable energy technologies. One of the major drawbacks of this new battery technology is corrosion, though new designs are in the works to curb it. Another disadvantage is that these batteries don't last as long as lithium-ion batteries. An overview of the benefits of removing cobalt from batteries. Video, CNBC. Cobalt-free lithium-ion batteries. How do they work? These batteries work like lithium-ion batteries, but they don't contain cobalt, which is typically used to stabilize the cathode in a lithium-ion battery. How will they be used? These batteries could be used in any device powered by a lithium-ion battery, but much of the focus is on developing cobalt-free batteries for electric vehicles. Currently being used by Tesla in some electric vehicle models, cobalt-free lithium-ion batteries could soon become a staple of Lamborghini's models, since the company has patented its new battery technology. Pros and cons of cobalt-free lithium-ion batteries. The main advantage of cobalt-free batteries is that they don't contain cobalt. Cobalt is incredibly expensive, and the mining of it is associated with human rights abuses. The United States Department of Energy is hoping to end the use of cobalt in lithium batteries by 2030. But alternatives to cobalt come with their own flaws as well. The process for mining and extracting cobalt can be toxic and dangerous, and another cobalt alternative known as TAQ is still new and requires more testing. For these reasons, companies may continue to rely on cobalt until they can establish other options. A look at how sodium-ion batteries can be an alternative to lithium-ion batteries. Video, DW Planet A. Sodium-ion batteries. How do they work? These batteries are similar to lithium-ion batteries, but instead use salt water as an electrolyte. How will they be used? These batteries are believed to be suitable for energy storage. As research on sodium-ion batteries progresses, the batteries could even go on to fuel faster charging in EVs, mobile devices, and space technology. Pros and cons of sodium-ion batteries. Despite low energy density, sodium-ion batteries are only able to store approximately 2/3 the amount of energy a lithium-ion battery of the same size can hold. It's much more affordable and very safe thanks to low risk of fire. It also performs better at lower temperatures than lithium-ion batteries. While sodium-ion batteries in the past have been too inefficient for electric vehicles, researchers are working on sodium-ion batteries with faster charging times. More on electric innovation. What are EVTOLs? Are they the future of aviation? Exploring the use of iron-air batteries as a form of energy storage. Video, Undecided with Matt Farrell. Iron-air batteries. How do they work? According to Popular Mechanics, iron-air batteries work by oxidizing iron using air to turn iron into rust to produce energy. During the battery's charging process, the cells are transformed back to iron through reverse oxidation. How will they be used? Iron-air batteries are great for energy storage, providing up to 100 hours of storage at 1/10 of the cost compared to lithium-ion batteries. Form Energy, an energy storage company, has finished constructing its plant in West Virginia and has received approval to build another site in Minnesota in partnership with Xcel Energy. Form Energy has also partnered with Puget Sound Energy to expand its technology in Washington State. All these developments allow Form Energy to provide crucial energy support to power plants. Pros and cons of iron-air batteries. These batteries are very affordable, given the abundance of iron and air in the world. In fact, they're up to 10 times cheaper, according to Popular Mechanics, and last up to 17 times longer. The only drawbacks are their large size and slow recharge time. An overview of zinc-based batteries and how they can be used for energy storage. Video, Undecided with Matt Farrell. Zinc-based batteries. How do they work? Zinc-based batteries work much like lithium-ion batteries with zinc ions flowing from the batteries anode to cathode. This class of new battery technology includes zinc bromine, zinc manganese dioxide, zinc air and zinc ion batteries. How will they be used? Zinc-based batteries could be used for solar energy storage because of their low rate of self-discharge. According to PV Magazine, a zinc air battery storage system was installed in a 32-building community in Queens, New York, in 2022. After receiving a $400 million loan from the Department of Energy, startup EOS Energy aims to improve climate technology and the U.S. grid system with its zinc-based batteries as well. Pros and cons of zinc-based batteries. These batteries are typically capable of storing an abundance of energy. Additionally, the materials used in their production are affordable, non-toxic, and readily available, according to PV Magazine. But researchers are still working to solve some technical problems related to these batteries, namely the potential for them to short-circuit. These batteries are also inefficient and expensive to produce, so more research is needed before they can be used more widely. An overview of why graphene batteries are the future of the EV industry. Video, Ultium Tech. Graphene batteries. How do they work? Graphene batteries consist of cathodes that are a hybrid of solid-state materials and graphene, which is made up of a thin layer of carbon atoms arranged in a honeycomb structure. How will they be used? Graphene batteries are viewed as a major upgrade to lithium-ion batteries and are expected to reshape the EV industry by the next decade. Everyday devices like smartphones and computers could also be equipped with graphene batteries to improve their performance. Pros and cons of graphene batteries. Graphene batteries are much more conductive than their lithium-ion counterparts, leading to faster charging in devices and EVs, increased battery capacity and extended battery lifespans. Graphene's sturdy structure also makes it a more reliable material than lithium-ion, lowering the risk of battery explosions and fires. The only setback to graphene batteries is their cost. Because companies have yet to figure out a way to mass-produce graphene batteries, the technology remains expensive and largely inaccessible to the general public for the time being. Battery swapping or battery switching is an electric vehicle technology that allows battery electric vehicles to quickly exchange a discharged battery pack for a fully charged one, rather than to recharge the vehicle via a charging station. Battery swapping is common in electric forklift applications. 1. Currently, Taiwanese electric scooter manufacturer Gogoro operates the largest battery swap network for electric mopeds, with nearly 11,000 GO stations in Taiwan, and 250 in mainland China. 234. Chinese luxury car maker NIO is the only major operator of automobile battery swapping stations for the public. The company has built around 2,250 battery swap stations around China and Europe, and the process takes 3 minutes from start to finish. 56. Previously, Renault and Tesla attempted to make their vehicles capable of swapping batteries. History. The Sunray and Cabalito on their way to Micronesia for a conference on global warming. The concept of an exchangeable battery service was proposed as early as 1896. It was first offered between 1910 and 1924, by Hartford Electric Light Company, through the GEVECO battery service, serving electric trucks. The vehicle owner purchased the vehicle, without a battery, from General Vehicle Company, GEVECO, part owned by General Electric. 7. The power was purchased from Hartford Electric in the form of an exchangeable battery. The vehicles and batteries were designed to facilitate a fast exchange. The owner paid a variable per mile charge and a monthly service fee to cover truck maintenance and storage. These vehicles covered more than 6 million miles. Beginning in 1917 and lasting a few years, a similar service operated in Chicago for owners of Milburn electric cars. 8. In 1993, Suntory developed a 2-seat 3-wheel electric vehicle called the Sunray, which came with a battery cartridge that swapped out in minutes at a battery swap station. 9. In 1995, Suntory added a motor scooter. 10. The company was later renamed Personal Electric Transports 11, PET. After 2000, the company developed an electric bus. In 2004, the company's 3-wheel stand-up EV won first place at the 5-day-long American Tour de Seoul Electric Vehicle Race 12 before closing in 2006. A rapid battery replacement system was implemented to service 50 electric buses at the 2008 Summer Olympics. 13. Some smaller schemes have attempted to popularize battery swapping with individual cities. Zoti Auto built a fleet 15 of M300F hatchbacks for a taxi fleet in Hangzhou, China. In 2011, one of these vehicles caught on fire after the battery pack in the trunk caught fire. An investigation later found that battery in question, as well as the connecting electronics in the truck, had become worn out from repeated loading and unloading of charged battery packs. The electric scheme was halted following the incident. 14. Azote EM300EV having its batteries replaced. Azote EM300EV having its batteries replaced. The batteries of Azote EM300EV being charged before being swapped. The batteries of Azote EM300EV being charged before being swapped. Wear and tear in the battery compartment of Azote EM300EV, located in the trunk. Wear and tear in the battery compartment of Azote EM300EV, located in the trunk. The Better Place network was the first modern attempt at making the battery switching model mainstream. The Renault Fluence CE was the first car enabled to adopt the approach and was offered in several countries, including those where no battery swap stations had been planned. 15. A Better Place battery switching station near Dver, Israel. Better Place launched its first battery swapping station in Israel, in Kiryat Ekron, near Rehovot in March 2011. The exchange process took 5 minutes. 16-17 subsequent battery swap stations were built in Denmark. Better Place filed for bankruptcy in Israel in May 2013. 1819. In 2012, Tesla started building a proprietary fast-charging Tesla supercharger network. 20 a year later. In June 2013, Tesla announced its plan to offer battery swapping. Tesla showed that a battery swap with the Model S took just over 90 seconds. 21-22 Elon Musk said the service would be offered at around $60 to $80 at June 2013 prices. The vehicle purchase included one battery pack. After a swap, the owner could later return and receive their battery pack fully charged. A second option would be to keep the swapped battery and pay the difference in value between the original and the replacement. Pricing was not announced. 21 In 2015 the company abandoned its sole swapping station, built at Harris Ranch, for lack of customer interest. 23. Other battery swapping service providers include Gogoro, Delta Electronics, BatSwap citation needed, Voltia, and SwapGo. 242526 By early 2022, NIO had built more than 850 swap stations in China, 27 up from 131 in 2020. 28 A station can cost $772,000 in China. A 90 kWh battery is charged at 60 kilowatts and can be swapped in 6 minutes. 27 China operates cement trucks where the heavy battery is swapped. 29 A battery swap system with a 2 mWh battery in each 20-foot, 6.1 m, shipping container. Powering a converted canal barge began operating in the Netherlands in 2021. 3031. In France, companies like Zway have implemented a battery swapping system for their electric scooters, enabling instant recharging in just 50 seconds through a network of battery swapping stations. This approach is gaining ground, especially in urban areas, as it promotes sustainable transportation, while addressing the limitations of traditional battery charging methods. In 2024, Zway reached 1 million swaps and became the European leader in battery swapping. Open source hardware, OSH, OSHW, consists of physical artifacts of technology designed and offered by the Open Design Movement. Both free and open source software, FOSS, and open source hardware are created by this open source culture movement and apply a like concept to a variety of components. It is sometimes, thus, referred to as FOSH, free and open source hardware. The term usually means that information about the hardware is easily discerned so that others can make it, coupling it closely to the maker movement. 1 Hardware design, i.e. mechanical drawings, schematics, bills of material, PCB, layout data, HDL source CODE2 and integrated circuit layout data, in addition to the software that drives the hardware, are all released under Free Libre terms. The original sharer gains feedback and potentially improvements on the design from the FOSH community. There is now significant evidence that such sharing can drive a high return on investment for the scientific community. Point 3. It is not enough to merely use an open source license, an open source product or project will follow. Open source principles, such as modular design and community collaboration. Point 456. Since the rise of reconfigurable programmable logic devices, sharing of logic designs has been a form of open source hardware. Instead of the schematics, hardware description language, HDL, code is shared. HDL descriptions are commonly used to set up system-on-a-chip systems either in field programmable gate arrays, FPGA, or directly in application-specific integrated circuit, ASIC, designs. HDL modules, when distributed, are called semiconductor intellectual property cores, also known as IP cores. Open source hardware also helps alleviate the issue of proprietary device drivers for the free and open source software community. However, it is not a prerequisite for it, and should not be confused with the concept of open documentation for proprietary hardware, which is already sufficient for writing FLOSS device drivers and complete operating systems. Point 78. The difference between the two concepts is that OSH includes both the instructions on how to replicate the hardware itself as well as the information on communication protocols that the software, usually in the form of device drivers, must use in order to communicate with the hardware, often called register documentation, or open documentation for hardware. 7, whereas open source friendly proprietary hardware would only include the latter without including the former. History. OpenHardware.org logo, 2013. OSHWA logo. The first hardware-focused open-source activities were started around 1997 by Bruce Perens, creator of the open source definition, co-founder of the Open Source Initiative, and a ham radio operator. He launched the Open Hardware Certification Program, which had the goal of allowing hardware manufacturers to self-certify their products as open. 910. Shortly after the launch of the Open Hardware Certification Program, David Freeman announced the Open Hardware Specification Project, OHSpec, another attempt at licensing hardware components whose interfaces are available publicly and of creating an entirely new computing platform as an alternative to proprietary computing systems. 11. In early 1999, Separkiani, Ryan Valance and Samir Nafeh joined efforts to apply the open-source philosophy to machine design applications. Together, they established the Open Design Foundation, ODF, 12 as a non-profit corporation and set out to develop an open design definition. However, most of these activities faded out after a few years. A free hardware organization, known as FreeIO, was started in the late 1990s by Dale Martin, who also launched a FreeIO website in early 2000. In the early to mid-2000s, FreeIO was a focus of free open hardware designs released under the new general public license. The FreeIO project advocated the concept of free hardware and proposed 4 freedoms that such hardware provided to users, based on the similar freedoms provided by free software licenses. 13. The designs gained some notoriety due to Martin's naming scheme, in which each free hardware project was given the name of a breakfast food, such as donut, flapjack, toast, etc. Martin's projects attracted a variety of hardware and software developers as well as other volunteers. Development of new open hardware designs at FreeIO ended in 2007 when Martin died of pancreatic cancer, but the existing designs remain available from the organization's website. 14. By the mid-2000s, open source hardware again became a hub of activity due to the emergence of several major open source hardware projects and companies, such as OpenCores, RepRap, 3D printing, Arduino, Adafruit, SparkFun, and Open Source Ecology. In 2007, Perens reactivated the OpenHardware.org website, but it's currently, August 2023, inactive. Following the Open Graphics project, an effort to design, implement, and manufacture a free and open 3D graphics chipset and reference graphics card, Timothy Miller suggested the creation of an organization to safeguard the interests of the Open Graphics project community. Thus, Patrick McNamara founded the Open Hardware Foundation, OHF, in 2007.15. The Tucson Amateur Packet Radio Corporation, TAPR, founded in 1982 as a non-profit organization of amateur radio operators with the goals of supporting RD efforts in the area of amateur digital communications, created in 2007 the first open hardware license, the TAPR Open Hardware License. The OSI President Eric S. Raymond expressed some concerns about certain aspects of the OL and decided to not review the license. 16. Around 2010, in context of the Freedom Defined project, the open hardware definition was created as collaborative work of MANY17 and is accepted as of 2016 by dozens of organizations and companies. 18. In July 2011, CERN, European Organization for Nuclear Research, released an open-source hardware license, CERN-OL. Javier Serrano, an engineer at CERN's Beams department and the founder of the Open Hardware Repository, explained, by sharing designs openly, CERN expects to improve the quality of designs through peer review and to guarantee their users, including commercial companies, the freedom to study, modify, and manufacture them, leading to better hardware and less duplication of efforts. 19. While initially drafted to address CERN-specific concerns, such as tracing the impact of the organization's research, in its current form it can be used by anyone developing open-source hardware. 20. Following the 2011 Open Hardware Summit and after heated debates on licenses and what constitutes open-source hardware, Bruce Perens abandoned the OSHW definition and the concerted efforts of those involved with it. 21. OpenHardware.org, led by Bruce Perens, promotes and identifies practices that meet all the combined requirements of the open-source hardware definition, the open source definition, and the 4 freedoms of the Free Software Foundation. 22. Since 2014, OpenHardware.org is not online and seems to have ceased activity. 23. The Open Source Hardware Association, OSHWA, at oshwa.org acts as hub of open-source hardware activity of all genres, while cooperating with other entities such as TAPR, CERN, and OSI. The OSHWA was established as an organization in June 2012 in Delaware and filed for tax exemption status in July 2013. 24. After some debates about trademark interferences with the OSI, in 2012 the OSHWA and the OSI signed a coexistence agreement. 25-26. The FOSSI Foundation is founded in 2015 as a UK-based non-profit to promote and protect the open source silicon chip movement, roughly a year after the official release of RISC-V architecture. 27. The Free Software Foundation has suggested an alternative free hardware definition derived from the 4 freedoms. 28-29. Forms of open source hardware. Explainer video for open science hardware. The term hardware in open source hardware has been historically used in opposition to the term software of open source software. That is, to refer to the electronic hardware on which the software runs, see previous section. However, as more and more non-electronic hardware products are made open source, for example WikiHouse, OpenBeam, or Hovelin, this term tends to be used back in its broader sense of physical product. The field of open source hardware has been shown to go beyond electronic hardware and to cover a larger range of product categories such as machine tools, vehicles, and medical equipment. 30. In that sense, hardware refers to any form of tangible product, be it electronic hardware, mechanical hardware, textile, or even construction hardware. The open source hardware OSHW. Definition 1.0 defines hardware as tangible artifacts, machines, devices, or other physical things. 31. Electronics. Electronics is one of the most popular types of open-source hardware. PCB-based designs can be published similarly to software as CAD files, which users can send directly to PCB fabrication companies and receive a build from them in the mail. Or users can obtain components and solder them together themselves. There are many companies that provide large varieties of open-source electronics such as SparkFun, Adafruit, and Seed. In addition, there are NPOs and companies that provide a specific open-source electronic components such as the Arduino Electronics prototyping platform. There are many examples of specialty open-source electronics such as low-cost voltage and current GMAW open-source 3D printer monitor 3233 and a robotics-assisted mass spectrometry assay platform. 3435 Open-source electronics finds various uses, including automation of chemical procedures. 3637 Chip design. RISC-V processor prototype, January 2013. Open standard chip designs are now common. OpenRISC, 2000, LGPL, OpenSpark, 2005, GPL v2. And RISC-V, 2010, Open Standard, free to implement for non-commercial purposes, are examples of free-to-use instruction set architecture. OpenCores is a large library of standard chip design subcomponents which can be combined into larger designs. Complete open-source software stacks and shuttle fabrication services are now available which can take OSH chip designs from hardware description languages to masks and ASIC fabrication on maker scale. Budgets. 38. Mechanics. Purely mechanical OSH designs include mechanical components, machine tools, and vehicles. Open source ecology is a large project which seeks to develop a complete ecosystem of mechanical tools and components which aim to be able to replicate themselves. Open source vehicles have also been developed, including bicycles like XYZ space frame vehicles and cars such as the Tabby OS vehicle. Mechatronics. Most OSH systems combine elements of electronics and mechanics to form mechatronics systems. A large range of open-source mechatronic products have been developed, including machine tools, musical instruments, and medical equipment. 30. Examples of open-source machine tools include 3D printers such as RepRap, Prusa, and Ultimaker, 3D printer filament extruders such as Polystruder 39XR Pro, as well as the laser cutter LaserSor. Examples of open-source medical equipment include open-source ventilators, the Echo stethoscope, ECOPEN, and a wide range of prosthetic hands listed in the review study by 10KT.AL40, e.g. Open Bionics prosthetic hands. Open source robotics combines open source hardware mechatronics with open source AI and control software. Other examples of open source hardware products can also be found to a lesser extent in construction, WikiHouse, textile, Kit 0 km, and firearms, 3D printed firearm, defense distributed licenses. Rather than creating a new license, some open-source hardware projects use existing, free and open source software licenses. 41 These licenses may not accord well with patent law. 42 Later, several new licenses were proposed, designed to address issues specific to hardware design. 43 In these licenses, many of the fundamental principles expressed in open-source software, OSS, licenses have been ported to their counterpart hardware projects. New hardware licenses are often explained as the hardware equivalent of a well-known OSS license, such as the GPL, LGPL, or BSD license. Despite superficial similarities to software licenses, most hardware licenses are fundamentally different. By nature, they typically rely more heavily on patent law than on copyright law, as many hardware designs are not copyrightable. Point 44. Whereas a copyright license may control the distribution of the source code or design documents, a patent license may control the use and manufacturing of the physical device built from the design documents. This distinction is explicitly mentioned in the preamble of the TAPR Open Hardware License. Those who benefit from an old design may not bring lawsuits claiming that design infringes their patents or other intellectual property. TAPR Open Hardware License 45. Noteworthy licenses include the TAPR Open Hardware License, drafted by attorney John Ackerman, reviewed by OSS community leaders Bruce Perrins and Eric S. Raymond, and discussed by hundreds of volunteers in an open community discussion. 4616. Balloon Open Hardware License, used by all projects in the Balloon project. Although originally a software license, OpenCores encourages the LGPL Hardware Design Public License, written by Graham Seaman, admin of OpenCollector.org. In March 2011, CERN released the CERN Open Hardware License, OL 47, intended for use with the Open Hardware Repository 48 and other projects. The SolderPad License 49 is a version of the Apache License version 2.0, amended by lawyer Andrew Katz to render it more appropriate for hardware use. The Open Source Hardware Association recommends 7 licenses which follow their open source hardware definition. Point 50. From the general copyleft licenses, the new General Public License, GPL, and Creative Commons Attribution Share Alike license. From the hardware-specific copyleft licenses, the CERN Open Hardware License, OL, and TAPR Open Hardware License, OL, and from the permissive licenses, the FreeBSD license, the MIT license, and the Creative Commons Attribution License. Point 51. OpenHardware.org recommended in 2012 the TAPR Open Hardware License, Creative Commons by SA 3.0 and GPL 3.0 license. Point 52. Organizations tend to rally around a shared license. For example, OpenCores prefers the LGPL or a modified BSD license. 53. FreeCores insists on the GPL. 54. Open Hardware Foundation promotes copyleft or other permissive licenses. 55. The Open Graphics Project USES 56. A variety of licenses, including the MIT license, GPL, and a proprietary license. 57. And the Balloon project wrote their own license. Point 58. Development. The OSHW, Open Source Hardware, logo silkscreened on an unpopulated PCB. The adjective open source not only refers to a specific set of freedoms applying to a product, but also generally presupposes that the product is the object or the result of a process that relies on the contributions of geographically dispersed developers via the Internet. Point 59. In practice, however, in both fields of open source hardware and open source software, products may either be the result of a development process performed by a closed team in a private setting or by a community in a public environment, the first case being more frequent than the second, which is more challenging. Point 30. Establishing a community-based product development process faces several challenges, such as to find appropriate product data management tools, document not only the product but also the development process itself, accepting losing ubiquitous control over the project, ensure continuity in a context of fickle participation of voluntary project members, among others. Point 60. The Arduino Diasimila, another popular and early open source hardware design. One of the major differences between developing open source software and developing open source hardware is that hardware results in tangible outputs, which cost money to prototype and manufacture. As a result, the phrase free as in speech, not as in beer 61, more formally known as Gratis versus Libra, distinguishes between the idea of zero cost and the freedom to use and modify information. While open source hardware faces challenges in minimizing cost and reducing financial risks for individual project developers, some community members have proposed models to address these NEDS 6.2 given. There are initiatives to develop sustainable community funding mechanisms, such as the Open Source Hardware Central Bank. Extensive discussion has taken place on ways to make open source hardware as accessible as open source software. Providing clear and detailed product documentation is an essential factor facilitating product replication and collaboration in hardware development projects. Practical guides have been developed to help practitioners to do so. 63 Another option is to design products so they are easy to replicate, as exemplified in the concept of open source appropriate technology. 64. The process of developing open source hardware in a community-based setting is alternatively called open design, open source development. 65 or open source product development. 66 All these terms are examples of the open source model applicable for the development of any product, including software, hardware, cultural and educational. Does open design and open source hardware design process involves new design practices, or raises requirements for new tools? Is the question of openness really key in OSH? 67 See here for a delineation of these terms. A major contributor to the production of open source hardware product designs is the scientific community. There has been considerable work to produce open source hardware for scientific hardware using a combination of open source electronics and 3D printing. 686970 Other sources of open source hardware production are vendors of chips and other electronic components sponsoring contests with the provision that the participants and winners must share their designs. Circuit Seller magazine organizes some of these contests. Open Source Labs. A guide has been published, Open Source Lab, book, by Joshua Pierce, on using open source electronics and 3D printing to make open source labs. Today, scientists are creating many such labs. Examples include Boston Open Source Science Laboratory, Somerville, Massachusetts. BYU Open Source Lab, Brigham Young University 71. Michigan TECH 72. National Tsinghua University 73. OSU Open Source Lab, Oregon State University. Open Source Research Lab, University of Texas at El Paso. Business models. Open hardware companies are experimenting with business models. 74 For example, LittleBits implements open source business models by making available the circuit designs in each electronics module, in accordance with the CERN Open Hardware License version January 2, 75. Another example is Arduino, which registered its name as a trademark. Others may manufacture products from Arduino designs but cannot call the products Arduino products. 76 There are many applicable business models for implementing some open source hardware even in traditional firms. For example, to accelerate development and technical innovation, the photovoltaic industry has experimented with partnerships, franchises, secondary supplier and completely open source models. 77 Recently, many open source hardware projects have been funded via crowdfunding on platforms such as Indiegogo, Kickstarter, or CrowdSupply. 78 Reception and impact. Richard Stallman, the founder of the free software movement, was in 1999 skeptical on the idea and relevance of free hardware, his terminology for what is now known as open source hardware. 79 In a 2015 article in Wired magazine, he modified this attitude. He acknowledged the importance of free hardware, but still saw no ethical parallel with free software. 28 Also, Stallman prefers the term free hardware design over open source hardware, a request which is consistent with his earlier rejection of the term open source software. See also alternative terms for free software. 28 Other authors, such as Professor Joshua Pierce, have argued there is an ethical imperative for open Source hardware specifically with respect to open source appropriate technology for sustainable development. 80 In 2014, he also wrote the book Open Source Lab, How to Build Your Own Hardware and Reduce Research Costs, which details the development of free and open source hardware primarily for scientists and university faculty. 81 Pierce in partnership with Elsevier introduced a scientific journal Hardware X. It has featured many examples of applications of open source hardware for scientific purposes. Further, Vasilis Kostakis et al. Have argued that open source hardware may promote values of equity, diversity, and sustainability. Open source hardware initiative transcend traditional dichotomies of global, local, urban, rural, and developed developing contexts. They may leverage cultural differences, environmental conditions, and local needs resources, while embracing hyperconnectivity, to foster sustainability and collaboration rather than conflict. 82 However, open source hardware does face some challenges and contradictions. It must navigate tensions between inclusiveness, standardization, and functionality. 82 Additionally, while open source hardware may reduce pressure on natural resources and local populations, it still relies on energy and material-intensive infrastructures, such as the Internet. Despite these complexities, Kostakis et al. Argue, the open-source hardware framework can serve as a catalyst for connecting and unifying diverse local initiatives under radical narratives, thus inspiring genuine change. 82 OSH has grown as an academic field through the two journals Journal of Open Hardware, JOE, and Hardware X. These journals compete to publish the best OSH designs, and each define their own requirements for what constitutes acceptable quality of design documents, including specific requirements for build instructions, bill of materials, CAD files, and licenses. These requirements are often used by other OSH projects to define how to do an OSH release. These journals also publish papers contributing to the debate about how OSH should be defined and used. CNC Reader Rex here. For other uses, see CNC, disambiguation. Numerics Reader Rex here. For the field of computer science, see numerical analysis. A CNC machine that operates on wood. CNC machines typically use some kind of coolant, typically a water-miscible oil, to keep the tool and parts from getting hot. A CNC metal lathe with the door open. In machining, numerical control, also called computer numerical control, CNC, one is the automated control of tools by means of a computer. 2 It is used to operate tools such as drills, lathes, mills, grinders, routers, and 3D printers. CNC transforms a piece of material, metal, plastic, wood, ceramic, stone, or composite, into a specified shape by following coded programmed instructions and without a manual operator directly controlling the machining operation. A CNC machine is a motorized maneuverable tool and often a motorized maneuverable platform, which are both controlled by a computer, according to specific input instructions. Instructions are delivered to a CNC machine in the form of a sequential program of machine control instructions such as G-code and M-code, and then executed. The program can be written by a person or, far more often, generated by graphical computer-aided design, CAD, or computer-aided manufacturing, CAM, software. In the case of 3D printers, the part to be printed is sliced before the instructions, or the program, are generated. 3D printers also use G-code. 3 CNC offers greatly increased productivity over non-computerized machining for repetitive production, where the machine must be manually controlled, e.g. using devices such as hand wheels or levers, or mechanically controlled by prefabricated pattern guides, see pantograph mill. However, these Advantages come at significant cost in terms of both capital expenditure and job setup time. For some prototyping and small batch jobs, a good machine operator can have parts finished to a high standard, whilst a CNC workflow is still in setup. In modern CNC systems, the design of a mechanical part and its manufacturing program are highly automated. The part's mechanical dimensions are defined using CAD software and then translated into manufacturing directives by CAM software. The resulting directives are transformed, by post-processor software, into the specific commands necessary for a particular machine to produce the component and then are loaded into the CNC machine. Since any particular component might require the use of several different tools, drills, saws, touch probes, etc., modern machines often combine multiple tools into a single cell. In other installations, several different machines are used with an external controller and human or robotic operators that move the component from machine to machine. In either case, the series of steps needed to produce any part is highly automated and produces a part that meets every specification in the original CAD drawing, where each specification includes a tolerance description. Motion is controlling multiple axes, normally at least two, X and Y, 4 and a tool spindle that moves in the Z depth. The position of the tool is driven by direct drive stepper motors or servo motors to provide highly accurate movements, or in older designs, motors through a series of step-down gears. Open-loop control works as long as the forces are kept small enough and speeds are not too great. On commercial metalworking machines, closed-loop controls are standard and required to provide the accuracy, speed, and repeatability demanded. Parts description. As the controller hardware evolved, the mills themselves also evolved. One change has been to enclose the entire mechanism in a large box as a safety measure, with safety glass in the doors to permit the operator to monitor the machine's function, often with additional safety interlocks to ensure the operator is far enough from the working piece for safe operation. Most new CNC systems built today are 100 electronically controlled. CNC-like systems are used for any process that can be described as movements and operations. These include laser cutting, welding, friction stir welding, ultrasonic welding, flame and plasma cutting, bending, spinning, hole punching, pinning, gluing, fabric cutting, sewing, tape and fiber placement, routing, picking and placing, and sawing. History. Main article, History of Numerical Control. The first CNC machines were built in the 1940s and 1950s, based on existing tools that were modified with motors that moved the tool or part to follow points fed into the system on punched tape. 3 These early servo mechanisms were rapidly augmented with analog and digital computers, creating the modern CNC machine tools that have revolutionized machining processes. Today, now the CNC in the processing manufacturing field has been very extensive, not only the traditional milling and turning, other machines and equipment are also installed with the corresponding CNC, which makes the manufacturing industry in its support, greatly improving the quality and efficiency. Of course, the latest trend in CNC 5 is to combine traditional subtractive manufacturing with additive manufacturing, 3D printing, to create a new manufacturing method. 6. Hybrid additive subtractive manufacturing, HASM. 7 Another trend is the combination of AI, using a large number of sensors, with the goal of achieving flexible manufacturing. 8. Examples of CNC machines. CNC machine description image. Mill translates programs consisting of specific numbers and letters to move the spindle, or workpiece, to various locations and depths. Can either be a vertical milling center, VMC, or a horizontal milling center, depending on the orientation of the spindle. Many use G-code Functions include face milling, shoulder milling, tapping, drilling, and some even offer turning. Today, CNC mills can have 3 to 6 axes. Most CNC mills require placing the workpiece on or in them and must be at least as big as the workpiece, but new 3-axis machines are being produced that are much smaller. Lathe cuts workpieces while they are rotated. Makes fast, precision cuts, generally using indexable tools and drills. Effective for complicated programs designed to make parts that would be unfeasible to make on manual lathes. Similar control specifications to CNC mills and can often read G code. Generally have 2 axes, X and Z, but newer models have more axes, allowing for more advanced jobs to be machined. Most modern lathes have live tooling, allowing for limited milling operations to take place without having to remove the part from the lathe spindle. Second operations can be completed by using a sub-spindle, which is coaxial to the main spindle, but faces the other direction. This allows the part to be removed from the main spindle, and for additional features to be machined in the back side of the part. Plasma cutter involves cutting a material using a plasma torch. Commonly used to cut steel and other metals, but can be used on a variety of materials. In this process, gas, such as compressed air, is blown at high speed out of a nozzle. At the same time, an electrical arc is formed through that gas from the nozzle to the surface being cut, turning some of that gas to plasma. The plasma is sufficiently hot to melt the material being cut and moves sufficiently fast to blow molten metal away from the cut. CNC plasma cutting. Electric discharge machining, EDM, also known as spark machining, spark eroding, burning, die sinking, or wire erosion, is a manufacturing process in which the desired shape is obtained using electrical discharges, sparks. Material is removed from the workpiece by a series of rapidly recurring current discharges between 2 electrodes, separated by a dielectric fluid and subject to an electric voltage. One of the electrodes is called the tool electrode, or simply the tool or electrode, while the other is called the workpiece electrode, or workpiece. EDM can be broadly divided into sinker-type processes, where the electrode is the positive shape of the resulting feature in the part, and the electric discharge erodes this feature into the part, resulting in the negative shape, and wire-type processes. Sinker processes are rather slow as compared to conventional machining, averaging on the order of 100 mm 3min9 as compared to 8x106 mm 3min. For conventional machining, but it can generate features that conventional machining cannot. Wire EDM operates by using a thin conductive wire, typically brass, as the electrode, and discharging as it runs past the part being machined. This is useful for complex profiles with inside 90-degree corners that would be challenging to machine with conventional methods. Sink or EDM. Electrolyte solution saturates the workpiece, and voltage is applied between the sinker top and workpiece bottom. Multi-spindle machine type of screw machine used in mass production. Considered to be highly efficient by increasing productivity through automation. Can efficiently cut materials into small pieces, while simultaneously utilizing a diversified set of tooling. Multi-spindle machines have multiple spindles on a drum that rotates on a horizontal or vertical axis. The drum contains a drill head which consists of several spindles that are mounted on ball bearings and driven by gears. There are 2 types of attachments for these drill heads, fixed or adjustable, depending on whether the center distance of the drilling spindle needs to be varied. 10. Water jet cutter, also known as a water jet, is a tool capable of slicing into metal or other materials, such as granite, by using a jet of water at high velocity and pressure, on the order of 60,000 psi, or a Mixture of water and an abrasive substance, such as garnet powder. It is often used during the fabrication or manufacture of parts for machinery and other devices. Water jet cutting is the preferred machining method when the materials being cut are sensitive to the high temperatures generated by other methods. It has found applications in a diverse number of industries from mining to aerospace, where it is used for operations such as cutting, shaping, carving, and reaming. The thickness of material processable via water jet machining is generally limited by the pressure of the water jet, and by the dispersion of the jet as it gets further from the nozzle. Some water jet cutters have a 5-axis cutting head, allowing for much more complex shapes to be cut, and to compensate for the angle of the curve to leave the angled wall on the stock instead of on the finished part. Thibaut water jet cutting machine. Water jet cutting machine. Punch press used to rapidly punch holes and cut thin materials, such as sheet metal, plywood, thin bar stock, and tubing. Punch presses are generally used when a CNC mill would be inefficient or unfeasible. CNC punch presses can come in the C-frame, where the sheet material is clamped onto a machining table and a hydraulic ram pushes down on the material, or they can come in a portal frame variant where bar stock tubing is fed into the machine. Punch machine at work. Other CNC tools. Many other tools have CNC variants, including 3D printing, CNC router, can cycle, cylindrical grinders, drills, embroidery machines, glass cutting, hot wire foam cutters, induction hardening machines, laser cutting, lathes, leather cutter, milling machine, oxy-fuel, plasma cutters, sheet metal works, turret punch, submerged arc welding, surface grinder, tube, pipe, and wire bending machines, vinyl cutter, water jet cutters, wood rooters, tool machine crashing. In CNC, a crash occurs when the machine moves in such a way that is harmful to the machine, tools, or parts being machined, sometimes resulting in bending or breakage of cutting tools, accessory clamps, vices, and fixtures, or causing damage to the machine itself by bending guide rails, breaking drive screws, or causing structural components to crack or deform under strain. A mild crash may not damage the machine or tools but may damage the part being machined so that it must be scrapped. Many CNC tools have no inherent sense of the absolute position of the table or tools when turned on. They must be manually homed or zeroed to have any reference to work from, and these limits are just for figuring out the location of the part to work with it and are no hard motion limit on the mechanism. It is often possible to drive the machine outside the physical bounds of its drive mechanism, resulting in a collision with itself or damage to the drive mechanism. Many machines implement control parameters limiting axis motion past a certain limit in addition to physical limit switches. However, these parameters can often be changed by the operator. Many CNC tools also do not know anything about their working environment. Machines may have load sensing systems on spindle and axis drives, but some do not. They blindly follow the machining code provided, and it is up to an operator to detect if a crash is either occurring or about to occur, and for the operator to manually abort the active process. Machines equipped with load sensors can stop axis or spindle movement in response to an overload condition, but this does not prevent a crash from occurring. It may only limit the damage resulting from the crash. Some crashes may not ever overload any axis or spindle drives. If the drive system is weaker than the machine's structural integrity, then the drive system simply pushes against the obstruction, and the drive motors slip in place. The machine tool may not detect the collision or the slipping, so for example the tool should now be at 210 mm on the x-axis, but is, In fact, at 32 mm where it hit the obstruction and kept slipping, all of the next tool motions will be off by 178 mm on the x-axis, and all future motions are now invalid, which may result in further collisions with clamps, vices, or the machine itself. This is common in open-loop stepper systems but is not possible in closed-loop systems unless mechanical slippage between the motor and drive mechanism has occurred. Instead, in a closed-loop system, the machine will continue to attempt to move against the load until either the drive motor goes into an overload condition or a servo motor fails to get to the desired position. Collision detection and avoidance are possible through the use of absolute position sensors, optical encoder strips or discs, to verify that motion occurred, or torque sensors or power draw sensors on the drive system to detect abnormal strain when the machine should just be moving and not cutting, but these are not a common component of most hobby CNC tools. Instead, most hobby CNC tools simply rely on the assumed accuracy of stepper motors that rotate a specific number of degrees in response to magnetic field changes. It is often assumed the stepper is perfectly accurate and never missteps, so tool position monitoring simply involves counting the number of pulses sent to the stepper over time. An alternate means of stepper position monitoring is usually not available, so crash or slip detection is not possible. Commercial CNC metalworking machines use closed-loop feedback controls for axis movement. In a closed-loop system, the controller monitors the actual position of each axis with an absolute or incremental encoder. Proper control programming will reduce the possibility of a crash, but it is still up to the operator and programmer to ensure that the machine is operated safely. However, during the 2000s and 2010s, the software for machining simulation has been maturing rapidly, and it is no longer uncommon for the entire machine tool envelope, including all axes, spindles, chucks, turrets, tool holders, tailstocks, fixtures, clamps, and stock, to be modeled accurately with 3D solid models, which allows the simulation software to predict fairly accurately whether a cycle will involve a crash. Although such simulation is not new, its accuracy and market penetration are changing considerably because of computing advancements. Point 11. Numerical precision and equipment backlash. Within the numerical systems of CNC programming, the code generator can assume that the controlled mechanism is always perfectly accurate, or that precision tolerances are identical for all cutting or movement directions. While the common use of ball screws on most modern NC machines eliminates the vast majority of backlash, it still must be taken into account. CNC tools with a large amount of mechanical backlash can still be highly precise if the drive or cutting mechanism is only driven to apply cutting force from one direction, and all driving systems are pressed tightly together in that one cutting direction. However, a CNC device with high backlash and a dull cutting tool can lead to cutter chatter and possible workpiece gouging. The backlash also affects the precision of some operations involving axis movement reversals during cutting, such as the milling of a circle, where axis motion is sinusoidal. However, this can be compensated for if the amount of backlash is precisely known by linear encoders or manual measurement. The high backlash mechanism itself is not necessarily relied on to be repeatedly precise for the cutting process, but some other reference object or precision surface may be used to zero the mechanism, by tightly applying pressure against the reference and setting that as the zero references for all following CNC encoded motions. This is similar to the manual machine tool method of clamping a micrometer onto a reference beam and adjusting the vernier dial to zero using that object as the reference. Citation needed. Positioning control system. In numerical control systems, the position of the tool is defined by a set of instructions called the part program. Positioning control is handled using either an open loop or a closed loop system. In an open loop system, communication takes place in one direction only, from the controller to the motor. In a closed loop system, feedback is provided to the controller so that it can correct for errors in position, velocity, and acceleration, which can arise due to variations in load or temperature. Open loop systems are generally cheaper but less accurate. Stepper motors can be used in both types of systems, while servo motors can only be used in closed systems. Cartesian coordinates. The GM code positions are all based on a three-dimensional Cartesian coordinate system. This system is a typical plane often seen in mathematics when graphing. This system is required to map out the machine tool paths and any other kind of actions that need to happen in a specific coordinate. Absolute coordinates are what are generally used more commonly for machines and represent the 0, 0, 0 point on the plane. This point is set on the stock material to give a starting point or home position before starting the actual machining. Coding. G-codes. G-codes are used to command specific movements of the machine, such as machine moves or drilling. Functions. The majority of G-code programs start with a % symbol on the first line, then followed by an O with a numerical name for the program, i.e. O0001, on the second line, then another % symbol on the last line of the program. The format for a G-code is the letter G, followed by 2 to 3 digits, for example G01. G-codes differ slightly between a mill and lathe application, for example G00 rapid motion positioning, G01 linear interpolation motion, G02 circular interpolation motion clockwise, G03 circular interpolation motion counterclockwise, G04 dwell, group 00, mill, G10 set offsets, group 00, mill, G12 circular pocketing clockwise, G13 circular pocketing counterclockwise. M-codes. Code miscellaneous functions, M-code, citation needed. M-codes are miscellaneous machine commands that do not command axis motion. The format for an M-code is the letter M followed by 2 to 3 digits, for example M01 operational stop, M02 end of program, M03 start spindle, clockwise, M04 start spindle, counterclockwise, M05 stop spindle, M06 tool change, M07 coolant on mist coolant, M08 flood coolant on, M09 coolant off, M10 chuck open, M11 chuck close, M12 spindle up, M13 both M03 M08 spindle clockwise rotation flood coolant, M14 both M04 M08 spindle counterclockwise rotation flood coolant, M15 both M05 M09 spindle stop and flood coolant off, M16 special tool call, M19 spindle orientate, M29 DNC mode, M30 program reset rewind, M38 door open, M39 door close, M40 spindle gear at middle, M41 low gear select, M42 high gear select, M53 retract spindle, raises tool spindle above current position to allow operator to do whatever they would need to do. M68 hydraulic chuck close, M69 hydraulic chuck open, M78 tailstock advancing, M79 tailstock reversing. Example: M05, spindle stops, G00x0.0y0.0, mill returns to origin. M30, program end. Having the correct speeds and feeds in the program provides for a more efficient and smoother product. Run. Incorrect speeds and feeds will cause damage to the tool, machine spindle, and even the product. The quickest and simplest way to find these numbers would be to use a calculator that can be found online. A formula can also be used to calculate the proper speeds and feeds for a material. These values can be found online or in Machinery's Handbook. 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 Found online or in Machinery's Handbook.